In this lecture, we shall see the definition of a topological space and some very basic examples. So let us begin by recalling the definition of power set. So let X be any set. Then the power set of X, denoted by P of X, is the set consisting of all subsets of X. In particular, it contains the empty set, which we usually denote phi, and the full set X, and the entire set X. So next we define what is a topology on a set X. Let X be a set. Let tau be a subset of the power set of X. Which satisfies the following three conditions. The first condition is that the empty set and the full set and the entire set X are in tau. So recall that tau is a subset of the power set of X, and so elements of tau are subsets of X. So the first condition that tau should satisfy is that it should contain the empty set and the entire set X. The second condition is that suppose u1, u2 up to un are finitely many elements of tau, that is, these are subsets of X which are elements of tau, then the subset of X, which is intersection of these ui's, I equal to 1 to n ui, should be a member of tau. This should also be in tau. And the third condition is let I be any set and suppose we are given a collection of elements ui's in tau for each I in I. So we're given a collection of subsets of x ui which are in tau for every I. Then the union then the set, the union of all these ui's should be in tau. So note that unlike the previous condition, that is condition 2, we do not demand that I is a finite set. Okay, so a subset tau contained in the power set of x which satisfies the above three conditions is called a topology on X. Okay. So often we shall write let x comma tau be a topological space by this we shall mean that X is a topological space that X is a set, sorry, and tau is a topology on X. So let us now see some examples of topologies. So the first example we are going to see is the trivial topology. So let X be any set and let tau be this subset of the power set of X. So that is tau consists of only two members, of only two elements. So let us check. There is a trivial check that tau satisfies the three conditions for being a topology. So clearly tau contains both the empty set and the full set X. Thus it satisfies the first condition. So let U1, let's check the second condition. So for this we need to take finitely many sets U1, U2 up to UN in tau, be a finite collection of elements of tau. So then we need to check that intersection of these UIs is in tau. So all the UI, since they are in tau, and tau has only two members, either the empty set or the full set, are either the empty set or all of X. If any one of the UI is empty, is the empty set, then clearly intersection I equal to 1 to n ui is the empty set, and so the intersection is in tau. So if none of the ui's are the empty set, then all the ui's, otherwise all the ui's are equal to x, in which case intersection of the ui's is equal to x, which is in tau. Thus, in both cases, in either case, I mean, we get that tau satisfies the second condition. So finally, let us check that it satisfies the third condition also. So to check the third condition, we need to take an arbitrary collection. Let ui for I in I be a collection of elements of tau. So we need to check that union I in I ui is in tau. So if all the ui's are the empty set, then the union is empty and so is in tau. On the other hand, if any one of the ui's, so each ui is either empty or is the full set. So if all the ui's are empty, then the union is also empty. So there's nothing to check. And on the other hand, if it is not the case that all the ui's are empty, then one of the ui's is non-empty, and so it is a full set X is equal to X. Then union I in I ui is equal to X, which is in tau. Thus, tau satisfies all three conditions for being a topology. So this topology is called the trivial topology. So this brings to an end the first example. So the next example we are going to see is the discrete topology. Again, let X be any set. And this time we take tau to be the entire power set. So in the previous example, tau consisted of only two elements. This time tau consists of all subsets of X. That is, tau consists of all subsets of X. Again, let us check that tau defines a topology on X. So we need to check that it satisfies those three conditions. So first, clearly tau contains the empty set and the full set X, as it contains all subsets of x by definition. So it satisfies the first condition. Let u1, u2, dot 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 up to un be a finite collection of elements of tau. Then the intersection is a subset of x, and so is in tau. So thus tau satisfies the second condition for being a topology. Now let's look at the third condition. So this is same. So let ui for I in some index set I be an arbitrary collection of members or elements of tau. Then again, the union of these ui's is a subset of x, and so is a member of tau. Thus, tau satisfies the third condition for being a topology. So this shows that tau defines the topology on X. So this topology is called the discrete topology. Finally, let us see one more example of a topology. This is called the finite complement topology. This example is slightly more interesting than the previous two ones. So here also, this is defined on any set X. Let X be a set, and let tau be those subsets of X, that is those elements of the power set, so that U is either empty, or when we take X minus U, this set should be finite. So let us check that tau defines a topology on X. So first, the empty set is in tau by definition. The full set X is in tau as it satisfies X minus X which is the empty set, is a finite set. I mean, the cardinality of the empty set is 0. Okay, so thus tau satisfies the first condition. So for the second condition, suppose that u1, u2, dot up to un is a finite collection of sets in tau. If any one of the ui's is the empty set, then the intersection. So we need to show that the intersection of these ui's is in tau. So if any one of these ui's is empty, then the intersection I equal to 1 to n ui is empty, and so is in tau. So let us assume that none of the ui's is empty. None of the ui is empty, which implies that for all I, x minus ui is a finite set. So look at the set, or rather we have, there's a trivial check, x minus intersection I equal to 1 to n ui is the union I equal to 1 to n of x minus ui. This left as an exercise. Now each of these is a finite set. So as a finite union, of finite sets is finite. This implies that x minus intersection I equal to 1 to n ui is a finite set. Thus, intersection I equal to 1 to n ui is in tau. So this shows that tau satisfies the second condition. So let us come to the third condition now. Suppose we are given a collection ui for I in I of elements of tau. Now, so then we need to show that the union I in I ui is in tau. So if all the ui are empty, then the union is also empty, and so is in tau. So let us assume that. So assume that there is a j in I such that uj is not empty, which means that x minus uj is a finite set. So again, we use the equality x minus union I in I ui is equal to intersection I in I x minus ui, and this is a subset of x minus uj, and this we know is a finite set. So as a subset of a finite set is finite, it follows that x minus this union is a finite set. So from this, it follows that union I in IUI is in tau. Thus, tau satisfies the third condition for being a topology. So this topology is, so thus tau defines a topology on X, and this topology is called the finite complement topology. So we will end the first lecture here. So in this lecture, we saw some examples of topologies on a general set X. In the next lecture, we will see examples of topologies on specific spaces which we often encounter. For example, the real line, the plane, Rn, etc.